Hello and welcome back. Today we will discuss the quarter wavelength impedance transforming or matching that we often call the ohmic matching. Well, what is it, the ohmic matching that I mentioned? Well, in many cases we have devices that have a characteristic impedance which is resistive, pure resistive, like the 50 ohm that we all know. There are some RFICs that has a different impedance than 50 ohm, like a 200 ohm differential, which is 100 ohm in relation to the ground, 100 in the positive terminal and 100 in the negative terminal. And differentially, this is 200. For example, it is possible also to have other types of impedances from devices. And usually, when a device is designed well, then the characteristic impedance or the termination impedance of it will be resistive. So in many cases, even though this is a very specific case of matching, in many cases we have a match between ohmic impedance to another ohmic impedance. Like in this example that you see here in the Smith chart, you see here we try to match 25 ohm to 50 ohm. We are starting from a point that is placed on the horizontal line, and we move along this horizontal line until we meet the 50 ohm. Of course, when we remember the movement that we can do along the Smith chart, there is no type of movement that takes us from right to left or from left to right. We have to go through the arcs or the circles on the Smith chart in order to move from the original point to the destination point in the center of the Smith chart. But eventually, we did move from the 25 ohm to the 50 ohm. If we are drawing a line between these 2 points, this is always on the horizontal line, in this case of matching. Well, if we need to make impedance matching, pure impedance, resistive impedance matching, then the classical approach is use a transformer. Here it is, the classical transformer has two coils. The ratio between the turns in the output relatively to the turns in the input, square on this ratio, multiplied by Zin will give us the output impedance that we see from this device. But, and there is always a but in RF design, I assume there is a but also in other engineering areas, but there is always but in RF. Solution is of using a transformer, a classical transformer is possible up to few gigahertz. There is the ceramic components that you can find up to few gigahertz, like 2 or 3, I would say, gigahertz. And there is the wire wound ferrite core transformer that you can find in, let's say, a few megahertz, a few hundreds of megahertz and below that. But if you work beyond this frequency, then you probably will have a problem to find the components that will do the transformation. In this case, you will have to design your transformer by yourself, and you won't be able to buy something that you can use. The components, in some cases, we can avoid using them because, of course, they cost money, and in some cases, we want to save this money. Of course, this is relatively to inductors and capacitors, the transformers are expensive. They are not so expensive, but they are relatively expensive. And there are applications where this difference in cost might be critical. And that's the main reason why in high frequencies and in some cases we won't be able to use the components, and we will need to design the transformer by ourselves. So what other options do we have? There's two other options that we can use. The first option is the quarter wave transformer. Quarter wave transformer, I mean the printed one, the microwave one without components at all, that you can implement in any type of transmission lines that you work with. Of course, if I'm not mentioning it, then I always relate my seminar to microstrip, which is the most common RF design infrastructure. And when we are talking about microstrip, then in the wavelength, the quarter wavelength transformer, it's only a printed line in the length of quarter wavelength. The other options that we have is use an LC transformer that is equivalent to the quarter wave transformer, and we will see how we can design the quarter wave that we need and move it to LC components in case we are working at low frequencies where we cannot afford the line length of the quarter wavelength, and we want to save this PCB area, etc. So here is the quarter wavelength. It's very simple actually if we look at it. Assume we have on the right side of this PCB part, we have a device with an impedance of Z1. The transmission line that reaches to this device also has an impedance of Z1 in order to maintain a good return loss, good matching to this device, on the right hand of this PCB. On the left hand, on the other hand, on the left side of the PCB, there is a connector or device which has an impedance of Z2. Okay, and the transmission line that goes from this device to the matching area also has an impedance of Z2. So we can look at it as we have Z2 on the right side and Z2 on the left side and Z1 on the right side. And we want to match between them. This is very simple. We design a quarter wavelength, which means 90 degrees in phase in the S21 phase transmission lines in between these two parts. And the impedance of this part has to be according to the formula that is written, meaning square of the multiplication between Z1 and Z2. And by that we will achieve a perfect matching between Z1 and Z2. Well, here there is an anecdote that I want to emphasize. Let's assume we have a very different impedance that we want to match. Let's say, let's take 250 ohm. And we have a very thin substrate. What will happen? We might run into a case that we cannot implement the quarter wavelength matching that we need. See this example. Let's say we have 200, we want to match it to 50 ohm. Then we take the formula that we've seen before, square 50 by 200, this is 100 ohm. Meaning the matching impedance, the quarter wavelength impedance has to be 100 ohm. If we take a substrate with a dielectric constant of 4, for instance, and let's say we have to work with very thin substrate, like let's say we are working with a 5 mil substrate, and then in the case, in the terms that I've mentioned, the 50 ohm on this substrate will be around 10 mil. Okay, but in order to implement 100 ohm, we will need something around 2.5 mil line, but we cannot implement 2.5 mil on a standard PCB. We want to keep it from 6 mil and above. So we have a problem to implement it, but there is a way to handle this, and we will see it in the next slide. Well, here is how we deal with this problem that we've mentioned in the previous slide. Here is our device. It has the impedance of 200 ohm, like we mentioned before, and we want to match it to 50 ohm. And we cannot design the 100 ohm quarter wavelength that we need. We are limited, let's say that for this example, we are limited by 70 ohm. I want you to remember that the narrower the line is, the higher its impedance. Let's say we cannot design a narrower line than the line that its impedance is 70 ohm. We cannot do that. So we are limited by 70 ohm. So what do? We connect, first we start by putting this 70 ohm connected to our device, and what impedance we will see from the input of this transmission line. This is quarter left line transmission line. Again, we are using the same formula that we have seen before, that the Z of the matching part is the square of the multiplication between the input and the output impedance. If we are using this formula, in this case, we will see that the input impedance of the first part is 24.5 ohm. And to match 24.5 ohm to 50 ohm, again, we use the same formula, the same Z matching equal to square multiply of 50 and 24.5. We will receive a matching part. Again, this is always quarter wavelength, but the impedance in this case will be 35 ohm. 35 ohm, it's something around twice as much as wide than 50 ohm, more or less, okay? And if we had this, if we are limited by 70 ohm, like in the example before that we used the thin substrate and all the problems that we mentioned, then we don't have a problem implementing a 35 ohm. Then we have two parts of quarter wavelength, and we did the matching that we need. Again, we took the 70 ohm, we matched 200 ohm to whatever came out of this, and then we took the new impedance and matched it to 50 ohm, which is feasible. And this we can do. When we are limited from below, when we are limited in the low impedances, when we have a case where the substrates are high, okay, or thick, then we might run into cases where the line width will be so wide that we won't be able to practically locate it in our design. Also, in high frequencies, there's also a limitation for the width of the line that we can use, because the width become non-neglected relatively to the length of the line. And this is not a simple model of a transmission line, and we have to consider that, and we have to take be very cautious when we design this in very high frequencies. But generally say, we are always, if we have a problem of when we are limited by the width of the impedance, we can use this method of dealing with the practical limitations we have on our PCB. Well, up until now we have discussed the distributed solution of the quarter wavelength. As we have seen in the previous sessions, there are always several ways of approaching a problem in RF, and in this case we also have the LC implementation of the quarter wavelength matching, or the ohmic matching. So let's look at this slide. Here we see in the upper diagram or the upper scheme, we can see the low pass unit, third order low pass unit, and in the lower one we can see a third order high pass unit. And we can design it in a way that it will act exactly like the quarter wavelength that we had before. What do I mean by act like the quarter wavelength? First, it has to act the same only in the frequency that we need it to act. Second, we want it to have the effect of the matching impedance that the quarter wavelength has. And the third thing is that we want it to have a 90 degrees delay. And what is the connection between the lumped element scheme and the distributed model. This is the formula that we have here. The capacitor size, both in both diagrams, the capacitor has to be, according to this formula, 1 divided by 2 pi frequency, and Zm, this is the impedance of the quarter wavelength that you would have wanted to design, and the inductor is Zm square multiplied by the capacitor that we have just calculated. This way we have identical devices that do the matching in the center frequency. Of course, they have a common solution in the frequency that we are working, which is marked here in F, with F. Okay, so in this case, there is also one anecdote that I want to emphasize. Sometimes we want to match impedances which are very different from each other. Then we might run to a case where the component values that we will get from our calculations will be very inconvenient, like, for instance, very close to the self-resonance frequency, not the one that are easy to work with. What can be done in this case? In this case, there is one trick that I want to get to know with. We take this pi network, which has inconvenient values, and we split it into 2 pi networks in series. But how we designed that? In order to determine what are the values of L1, L2, C1, 2, 3, and 4, we calculate, instead of taking F in our formula, like let's say we have a system in 1 gigahertz, instead of calculating 1 gigahertz, we calculate the values using 2 gigahertz, twice the frequency that we work with, and we get the values of L and C. We place the L and C in our location, put it in a simulator. This will be almost what we need. It won't be exactly, it will be almost. Of course, I'm not putting any emphasis here on math. I only give engineering tools on how to solve this issue of high value of components. Of course, there is a math. Of course, there is a math of filters. This is third order filter and this is fifth order filter, and we can get into this math and have 3 sessions on this only, but we don't get into this. We are putting emphasis only on the tools on how to resolve this. So we said we calculate the formula using twice the frequencies that we work with, and we place it in our location. It will be almost what we need. Then we make a very short optimization, and we will get values that are very close to what we have calculated. Of course, note that C2 and C3 here can be merged to one capacitor, of course. And when you do this optimization, you have to keep, in order to simplify the design and not to get into multiple values of components, you can do that using equal capacitors, meaning that C1, 2, 3, and 4 are the same capacitor, or meaning that C2 and C3 C2 and C3, when they are merged, they are twice as much than C1 and C4. But if you don't want to merge them, then C1, 2, 3, and 4 are equal. And L1 and L2 are equal as well. Do the optimization. This is very short and easy, and you will get a fifth order network that do the same matching as this third order network, but with much smaller components, much far from the self-resonance frequency, much more convenient to work with, and here we have a solution.